Hey guys, let's look at the net change theorem. The net change theorem says that if you're given some rate of change, or in other words, a derivative, if you take the integral of that thing, it gives you the net change from one point to another. And that's expressed like this. The integral from a to b of f prime of x dx is f of b minus f of a. And if you look at page 401 in the book, they give a bunch of different examples of situations where you could use this. But we are going to concentrate on things where we're looking at velocity and position. So I want to look at two things: net change in position and total distance traveled. And just for sort of a quick example of that, if I were to walk a mile down the road and then I walk back, then my net change in position is 0 because I'm back where I started. But my total distance traveled would be 2 miles because I did all that walking. And we're gonna use that sort of idea in here when we're looking at total distance versus net change. So recall, velocity is the rate of change of position, and velocity tells us speed and direction. Now we're going to keep things pretty simple in here and just use velocity as we're going to think about moving along a straight line. So the direction is basically going to be positive or negative. And this fact down here is pretty much taking the net change theorem and rewording it in terms of velocity and position. If you integrate velocity, that gives you the net change in position. So let's start with an example where I want to do several things. We've got a ball that's launched straight up in the air. Its initial velocity is 48 feet per second. And so the velocity of the ball t seconds after it's launched is given by this equation. Now, there are a few things I want to do, but the first thing I want to do is just find the height function. All right, now keep in mind, this is the velocity function. So if we let h of t be the height, then if we did h prime of t, that's going to be the velocity. And another way of writing that relationship there, h prime of t is velocity, would be h of t is the integral of velocity. So those two things really tell you the same thing. They're just written slightly different. So let's find h of t. H of t then is the integral of 48 minus 32t dt. So that's 48t minus 16t squared plus c. And that's our function for height. What about the c? Can we figure that out? Well, they did. The problem does give us a little bit of information. It says it's launched upward from ground level. So from ground level, that means that in the beginning of this problem, t is 0. And since it's at ground level, the height is 0. So we could use that to plug in down here and solve. This would give us c equals 0. I'm not going to write that down, but I will say how I did it. If you plug in the 0 here, h of t, if you plug in h of 0, you get 0 minus 0 plus c equals 0. So what we have here is h of t is 48t minus 16t squared. All right. Now let's look at that on Desmos. I've got it drawn here already. 48t minus 16t squared. And notice I restricted the time to go from 0 to 3 because that's the only time that this really applies. Because this is a ball, it's launched at time 0, and the equation telling its height or its velocity really only applies until the moment it hits the ground. At that point, things change. So anyway, this gives us the height of the ball at any time from from 0 to 3. And so I want to look at a couple of things here. The first question says, find the net change from t equals 0 to t equals 1. So let's do that. If I do that, I'm going to integrate 48 minus 32t from 0 to 1. Now really all that's going to do is find us the difference between the height here and the height here at 1. So just from looking at Desmos over there, it looks like the answer is going to be 32. But let's work it out and see. This gives me 48t minus 16t squared from 0 to 1. Let's plug those numbers in. You get 48 minus 16 for the 1. You get 0 minus 0 for the 0. So yeah, you get 32. And notice it's positive. That positive 32 means from t equals 0 to t equals 1, the change in height is 32. It's up 32. I'm going to change this step so that it's easier to deal with. Yeah. All right. Now this next thing, find the net change from t equals 1 to t equals 2. Let's just go through and use the net change theorem. We're going to go from 1 to 2 of 48 minus 32t dt. That gives me 48t minus 16t squared from 1 to 2. And when I plug this in, that's going to be, let's see, 48 times 2 minus 16 times 4 for plugging in the 2. When I plug in the 1, I just get 48 minus 16. And now, let's see, this first number, 48 times 2 minus 16 times 4 gives me 32. 48 minus 16 is also 32, and that gives me 0. So really, what that's doing, let me put in another thing here. B comma height at B what this is asking me now is find the net change in height between these 2 points here. And well, the net change in height there is obviously 0 because it starts at 32, goes up a little bit, and comes back down to 32, and then so the net change in height from t equals 1 to t equals 2 is 0. And we see that both from the graph looking at it and from this right here, the net change theorem. All right, now this next problem says find the total distance traveled by the ball from t equals 0 to t equals 3. All right, well, if I do that, let's see, I'm going to turn this point off. If I do that, we're trying to figure out what's the total difference in height that the ball travels going up and going down. And going up, when it reaches a maximum height of 36, and then it goes back to 0. So you can kind of look at this and see it goes up 36 and then down 36. So the total distance traveled from 0 to 3 is going to be 36 plus 36 is 72. So we can just answer it like that, 72. Of course, that's from looking at the graph and seeing all the niceness and everything. The way we would do this using the, what we'd have to do is split the time, from t equals 0 to t equals 3 at any places where, all right, now obviously on this picture, we want to stop when it's at the top because that's when it changes direction. And remember, the only places it can change direction is where the derivative is 0. So we need to split the time at any places where v of t equals 0. So let's see, v of t, that was 48 minus 32t. So if you solve this out, you get 48 is 32t. So t is 1.5. So what this tells us to do is we want to find the integral from 0 to 1.5. And then we want to find the integral from 1.5 to 3. If we add that up, we're going to get 0. What we want to do is we want to take the absolute value of both of these things. So let's do that. Now, this first one, integral from 0 to 1.5 of v of t. Now that's going to be h. Well, I'm tempted to make this quick, but I probably shouldn't do that on the first one. This right here, integral from 0 to 1.5 of 48 minus 32t dt is, let's see, 48t minus 16t squared from 0 to 1.5. If you plug that in, you get 48 times 1.5 minus 16 times 1.5 squared. Then you plug in the 0, you just get 0. So let's see, what is this? 48 times 1.5 minus 16 times 1.5 squared. Sure enough, it gives me 36. Okay, this one, I go from 1.5 to 3. In the interest of cutting a little bit of time off, I'm just going to go ahead and say if you work this out, the answer is negative 36. That's the distance that it travels during that second time. So the total distance traveled is absolute value of 36 plus absolute value of negative 36 is 72 feet. All right, so we're going to do a few more examples of this, and in the following examples, I'm going to cut some corners in a few places to make the computation not take so long. But I wanted to do this first one out at length, since it's the first example. So we will look at some additional examples in the next video.